Hello, I am Aryan, a Robotics Institute summer scholar at ALab under the mentorship of Dr. Chen Wang and Dr. Sebastian Sharon. I will be presenting the work AirLoc, which is object-based indoor relocalization. People might wonder why indoor relocalization is so important. But can you imagine if you have a indoor positioning system similar to what GPS does in outdoor scenes, and you can easily navigate in large indoor environments such as shopping mall, large offices, and supermarkets? That will be really cool, right? But there are some major challenges while performing indoor relocalization. Firstly, geometric-based maps are not very sufficient to carry out robust relocalization in indoor scenes, so there is a high need to adopt object-based relocalization method. The method behind using objects is, firstly, objects are simply more informative than geometry elements. And secondly, we can extract qualitative information from the position of objects and use this in qualitative information to perform tasks such as relocalization. There are two major contributions in this work. The first contribution is data generation, and the second contribution is the proposed novel methodology. Coming to the data generation section, we reviewed all the datasets present in the literature for indoor relocalization. These datasets include Places 365, MIT indoor scenes, and AD20K. But there are some challenges with all these datasets. Either they do not contain room level divisions, or they do not have semantic and depth data, or they have very less images from varying viewpoints. The images from varying viewpoints are really important to learn geometric information. To mitigate the issues with all these datasets, we generate our own dataset. We use Habitat Sim as a simulator. It supports 3D textured mesh, which looks like this. We use a MP3D textured mesh, MP3D dataset, which has 90 such 3D textured meshes, and we select 15 from them. For every textured mesh and for every room in a textured mesh, we sample 2500 random navigable points, and for all these random navigable points, we extract RGB depth and semantic information. In this way, we have a lot of images from varying viewpoints. We have the semantic and depth data, and we have room and building level divisions as well. Coming to the methodology, the first part is database construction. We take some k number of images, which can either be 2, 4, or 8 images, and pass it to an object encoder along with the semantic labels. The output of object encoder is the object descriptor for every object present in the image. So this is how we generate a database for our rooms, which is the object descriptors for objects present in the rooms. To dig deep into how object encoder works, we take an image, we pass it through a superpoint extractor, which extracts the key point and key point locations and key point descriptors. Along with the semantic image, we extract the object-wise key point features and key point descriptors. We pass all these object-wise key point descriptors to an object encoder, which further encodes it into a single object embedding. We tried multiple object encoders, which are graph convolution network, graph attention network, and NetVLAD. NetVLAD performs best out of all the tried object encoders, and it can also be seen that NetVLAD, even if NetVLAD is not trained on MP3D dataset, it generalizes very well to MP3D dataset. Coming to the main part of the methodology, which is the object matching approach, we generate the reference in the way described earlier, and we generate the query in the same way. So now we have object descriptors for the query image and the reference image. For every object in a query image, we match it with the objects present in the reference room, and the room having maximum similarity with the query object is considered as a match. Similarly, we take all the matches and sum their similarity up to make a similarity between the query image and the room. Now, We have a room similarity matrix where every column denotes the similarity of a query with all the rooms present in the database. The room having maximum similarity with the query is considered as a match. And this is how we localize our query into multiple rooms. Coming to the results, for the task of room level localization, we try multiple baselines and object matching approach performs best out of them. The baselines are: firstly, we use a netfilet-based object descriptor and graph attention network. Secondly, we use a netfilet-based object descriptor and encode it using graph convolution network. Third, we use a netfilet-based object descriptor and do arithmetic mean of all the object descriptors. And finally, we use a netfilet-based image descriptor, which is a very common approach in place recognition. We get 10% higher than the nearest baseline, which is a very great improvement. Coming to the future works of this work, firstly, we will learn the geometric relationship between objects to get our results more accurate. Secondly, we'll test our approach on real world. I would like to end this with a thank you note. I would like to thank Dr. Chen Wang and Professor Sebastian Scherer for their constant support and guidance throughout the program. Furthermore, I would like to thank Rachel Bursin and Dr. Joan Dolan and all my fellow risk cohort members for a wonderful summer experience.